Hey, good day folks. Today I'll create a project structure for simple C applications. Now, while there's a lot of really good modern system programming languages available, C is still fundamental and it is the de facto ABI. So in cases where we need to perform system calls against the operating system, we would need to understand how to perform those system calls in C. And in cases where we've got a project where different modules are written in different programming languages, C would be the glue that holds that entire project together. So each module would expose a C header, and that header can be imported into the other modules where their native bindings can be used to call the functionality on those modules. So let's start with a Hello World application. Now my preference is that all my source files need to be inside an src directory, and I've got another preference that my application entry point must be inside a main.c file. The application entry point is a main method, so it's going to have return type of int and the name's going to be main. Now the main method doesn't need a return statement, but this looks silly for me, so my preference is to always have a return statement when there is a return type. Also, the return value of 0 indicates that this application completed successfully. A non-zero value indicates that there was some sort of a failure. Now, to print output to the terminal, we need to call one of the standard C library functions. In this case, I'm going to call fprintf. Now the first parameter is just going to be the handle for the standard output. So that would print text to the terminal. There is a standard error that would also print text to the terminal. But in terms of scripting, standard error and standard out are two different channels, so we can split the output in scripts. The second parameter is the format string, so we can just apply the pattern that we want in the output. So we want the output to start with hello, then there's going to be some string that would be a parameter, and followed by an exclamation mark, and then we want to print a new line at the end. Now, after the second parameter, we can supply our parameters for the format string in the order that format specifiers are declared. So in this case, world for the string. Now, the thing that it's complaining about here is that there's no declaration for the fprintf function, and that's because I still need to include the appropriate header file from the standard C library. In this case, this is going to be include stdio.h, so stdio for standard IO. Anyway, let's have a look and see if this compiles. So my preference is that all build output should go inside a build directory. Now to compile the Hello World application, I'm going to use the clang compiler. An alternative is GCC. You can use GCC if you want. It's just I picked clang. Now we can say that the output of the compilation should go to our build folder. I'm going to call it our app. And now we can supply the input, which would be our main.c file. Okay, so that compiled successfully, and if we run the application, we can see Hello World. Now, building the application is something we would need to do often, so it makes sense for us to invest a little bit of time into a build system. Now, because this is only for simple applications, I'm just going to use GNU's Makefile. So this is a build system that can be used with multiple programming languages. The general idea here is we can have some sort of a target, then we can have our dependencies, and then we'll follow that by the commands to create the target from the dependencies. So what we're going to supply here is our default target is all, and that's going to depend on the creation of the build directory and then our application. So to create the build directory. We don't have any dependencies. All that need to run is mkdir build. And then to create the application, this depends on the source file. And now we just have the command that we would have used from the terminal. Righto. Now something else here. Typically the target need to be a file system artifact. Now we can tell Makefile that all doesn't have a file system artifact. So we just save it, there's this phony target. Now if we run make, it will tell us that there's nothing to do. If we just remove the app, make will rebuild the app. If we remove the build folder, make will create the build folder and build the application. Okay, so just a little bit of cleanup before we go on. I want to have a clean target, and what the clean target does is it will just remove all the build artifacts. And I want to use automatic variables. So instead of having to type out the target in the command, we'll just use the automatic variable for the target. And instead of having to type out all the dependencies, we can just use the automatic variable for the dependencies. So let's try it out. Make clean deletes the build directory. And if we now do make, it will build our application again. Now there are some features from C23 that I want to be able to use. For example, there is now a Boolean type in C, which, as we can see here, the editor doesn't know what to do with this bool keyword. And if we try to build, the compiler also doesn't know what to do with this. So the way to fix this is we need to use some compiler flags. So I'm going to go back into my Makefile. I'm going to say that we've got some C flags that I want to supply. And the flag that I'm interested in here is the standard need to be C23. Then we can go to the line where we call the C compiler. And we just supply all the C flags. So now the compiler is happy, so it can build the application with the C23 feature, but our editor is still unhappy. Now for the editor, I'm using the clang D language server, and we can supply some compiler flags to clang D through compile flags.txt. And in here, I'm just going to say std equal to C23. Now, every compiler flag does need to be on its own line. So if we want to add more, that would need to go on a second line. Cool. So now if we open the file again, we can see that the editor is happy with this new C23 feature. So this Boolean variable is unused, and what I want is I want the compiler to tell me when I do inappropriate things like unused variables. So for this, we can go back to our Makefile, and we can just add the WAll flag, which will tell the compiler to print out all warnings, and the WError flag that will tell the compiler to treat warnings as compilation failures. So now if we rebuild the application, we are going to get this compiler failure that there's an unused variable. Now at this point, the editor doesn't yet know that it should print these warnings. So we can go back to our compile flags, and I can just add the WAll over here. Now, at this point, I do need to restart the editor so it can reload the configuration for the language server. But when we open main again, we can see that the variable is unused, so I can remove it easily. And now if we rebuild the application, everything goes well. Now, because I'm often trying out something new in C applications, I do tend to make mistakes and I need some help with a debugger. So to demonstrate debugging, I'm going to introduce a memory access violation. This should give us a segmentation fault because we are trying to set something on a null pointer. So now if we build the application and we run it, we'll see that there's a segmentation fault. Now to debug an application that's compiled with CLang, we will use LLDB. If it was with the GNU compiler, we would be using GDB. And then we supply the path to the executable, and we can just tell it to run. Now the debugger introduced a breakpoint at the moment the segmentation fault happened. Now this might be difficult to translate the assembly instructions back to the C code, so we do need to include debug information into our application. And the way to do that, back in our Makefile, we just need to add a compiler flag -G, which will tell the compiler to include debug information in the executable. So now let's rebuild the application. And if we rerun the debugger, now we can see where the segmentation fault happened in our C code. Okay, so thanks to the information we got from the debugger, we can locate the problem, and we see what we need to do here is we need to allocate some memory first. And we need to supply the function declaration, which is inside stdlib. So now if we build the application and run it, everything seems fine, except it's not really fine. What we've got here is a memory leak. Now inside the main method, memory leaks are not really that bad, because once the method returns, the operating system will clean up all the open resources. But let's imagine for a moment this is inside some function in our code, where we've got this resource that's being allocated and it doesn't get freed up while the application's running. So we do need a compiler to help us a little bit here. And for this, we can add a compiler flag that we turn on the address sanitizer. So the flag for this is if sanitize equals address. So now if we clean and rebuild the application and we run it again, now the address sanitizer will tell us that we've got a memory leak. And we can quickly go and fix it. And all we need to do here is, once we're done using that memory, we just need to say free. So now if we make the application again, and we run it, everything's fine. Now we can have all our code inside the main.c file. There's nothing wrong with having C files of hundreds of thousands of lines of code. However, having it all in the main.c file can cause problems with things like unit testing. The main.c file already have an application entry point, so we can't link that unit to another unit that also have an application entry point. So realistically speaking, most applications would have at least two units. The unit with the application entry point and a unit with all the core logic that would be able to link against other units with application entry points. Now, the way that units would call functionality in other units is they will include a header file with the function declarations. So let's create a header file for our core unit. Now, a common problem that may occur with header files is when we've got diamond dependencies. So we've got multiple other header files that include the same header file. And then in our main.c file, we would include multiple header files. And so we have a situation where there could be multiple declarations of types and functions. Now, this could result in compilation failures. So the common way to work around this problem is with preprocessor macros, where we define a label, and if the label's already defined, then we would not include the code a second time. So let's implement that. So if not defined, and then the label would typically be the file name in uppercase, core H. Then what we're going to do is we'll define the label. And we need to end this block with an end if. Now, for this core module, I'm just going to declare an add function. And in our main file, what we can do is we can include the core header file. Now in this case, having the header file name in quotes means that it's going to be in the local search path. And we can demonstrate the usage of this. So if print so the format here is just going to be some number plus some other number equals to a number. So 2, 3, add 2, 3. Okay, now just in terms of compiling the main unit, the compiler will pass because it's got a declaration for add. But when the compiler tries to link everything together, the linking will fail because there's no definition for this function. So let's demonstrate that quickly. As we can see, the linker failed. Okay, so let's fix this by creating the definition for this function. So for this, I'm going to create a core.c file. Now, on the first line, what I typically do is I'd include the corresponding header file. Now, this is not strictly necessary in this case. The C compiler is clever enough to link up the definitions and declarations. The reason I typically do this is if I've got types declared in the header file, then I want those types in my C file. Okay, so let's apply the definition for the function. So we've got the add function, and it's just going to return the sum of those two numbers. Righto. Now at this point, if we try to build the file again, we're still going to see that linker problem. Now the reason for this is we still need to fix up our Makefile. So let's fix up the Makefile quickly. Okay, and a simple way to fix this is we're just going to say that one of the dependencies of the app is core.c. Okay, so now it compiles and it builds successfully. Let's run it. Cool, everything as expected. So there's a problem with the way we've got the build system at the moment, and that is that it doesn't know that it should rebuild the application when there's changes to our header file. So let's say, for example, maybe we had some constant over here and we change the value of that constant. When we type make, we would want the application to rebuild, but it doesn't. So just for comparison, if we make a change to the C file, even if it's just adding a comment, the build system knows that it should rebuild the application. Now, what we may intuitively want to do is we want to have the header file as a dependency for the application build target. Now, when we do this, what we'll find is that the compiler doesn't know how to deal with this header file in these input sources. I think it thinks that we may want to generate a pre-compiled header, which is something I'm not going to do for a simple application. Now, let's look at how we can fix this. So going back to our Makefile, what I would want to do here, instead of including the entire dependency list, I want to say, let's just include the first dependency, which is the source main. And then from here on, I want to use core.c as an additional parameter to the compiler. So this should solve the trick. Okay, now when we now try to modify the header file, okay, let's change that to 20. It knows that it should rebuild the application, which is what we want. But I think I can clean this up a bit. So instead of having to retype things multiple times, I'm going to introduce some additional variables. So first up, we've got sources, which is our core file, and then we've got headers. Okay, so we want to supply all the sources to the compiler. And similarly, instead of typing out the headers, I'm going to supply the headers. Okay, so let's check that it works. Okay, so everything's fine. Let's make another change to the header file. Okay, it knows to rebuild. Let's make a change to the source files. Wrong source file. It knows that it should rebuild. And if we didn't change anything, it knows that the application doesn't need to be rebuilt. Okay, so this turned out to be another long video. What I wanted to do next is unit testing, but that's also quite a big topic, so I think it's best that I split this up into a multi-part video. If you like this video, click on the like button. If you want to see more, click subscribe, and I'll see you next time. Ciao.